Hello, and welcome to the workshop by RoboRacers 16481. Within this workshop, we will be learning about a PID, a closed-loop control system. There will be two sections to this workshop, one explaining the mechanics and the math behind the PID, and the other will be explaining the code and test running the PID in Java running on the FTC SDK 7.2. In this section, we will be learning about how a PID works. Closed-loop controller. To start, we need to understand a closed-loop controller. A closed-loop control system is a mechanical or electronic system that can achieve a desired position by looking at the current position and calculating the correction needed to be applied to achieve the desired position. Some of the main terminologies that we'll be using within this slideshow. Set point. Set point is the desired position of your robot. Measured process variable. This is the current position of your robot acquired from the sensors. Measured error. Measured error is the difference between the set point and the measured process variable. This can be a negative or positive value, depending on the position of your robot. Control variable, or system input, is the correction applied to move the robot from the current position to the target position. This is trying to reduce the error to 0. Gain constant. The gain constant is the sensitivity of the selected controller. Rise time. The time that it takes for the PID to reach the target position. Settling time. The time that is taken by the PID controller to stabilize. What is a PID? A PID controller is a control loop mechanism that is used to calculate and control variables. It's used in many industrial processes such as regulating flow, temperature, etc. It has three parts: the proportional, integral, and derivative. We will go into these in a deeper level within the next few slides. The proportional controller. Proportional controller. A proportional controller is the simplest of all, and it looks at the current error and calculates a correction value to be applied to lower the error. Before applying the correction, it is multiplied with the gain constant Kp to adjust the correction applied. The equation to calculate proportional correction is your Kp gain constant multiplied by your measured error. There are two major problems when using an only proportional controller. One is that the oscillation, where the PID is stuck in a repetitive movement without stopping at its target position. And the second is steady state error, which is when the correction applied is not enough to change the current position. Next, we'll move into the integral controller. When steady state error occurs, integral correction applies more and more correction over time to get the target out of steady state error. Integral correction looks in the past and sums errors over time like memory. We can calculate the integral correction by multiplying the integral gain by the measured error plus the previous integral correction. The integral term accelerates the movement of the process towards the set point and eliminates the steady state error that occurs with a pure proportional controller. However, since the integral term responds to accumulated errors from the past, it can cause a present value to overshoot the set point value. Issues that can occur with the integral oscillation and stability decrease. We will now work our way into the third and final controller, the derivative controller. To address the overshoot and oscillation issue, we can use a derivative controller. The derivative controller reduces the correction as current position reaches the set position. The derivative correction is calculated by finding the rate of change of the error over time. The derivative action predicts the future system behavior based on the rate of change, thus minimizing the overshoot and improve the settling time and stability of the system. The equation for the derivative can be seen on the slide. The tuning of these three values can be seen within the following animation. You can see how each value affects the system response. These are all the basic controllers that you will need to know moving forward when learning PID. Always keep these in the back of your mind as you progress towards learning the full functionality and uses for the PID. These are the sources that we got most of our information from. Thank you.
Alright, so now I'm going to go over the code. First of all, we have to have our standard imports: linear op mode, teleop, distance sensors, servo, and these two are my system specific because I'm using a distance sensor and a servo. We have time elapsed. We do our math based off of the time elapsed. We have the FTC dashboard, which we use to tune configurations, and all of these are just parts of the FTC dashboard, and this is part of the rev sensor, just our standard teleop. So I'm going to define my sensor, I'm going to define my servo motor, and I will come back to these values. So this is the KP, which is the proportional gain, this is the integral gain, and this is the derivative gain. You modify these values to tune your PID, which I will go into with the FTC dashboard, and I can show you a nice and easy way to tune your PID. So we start off with our errors as 0, just these do change later, but just for now they're 0. All of these are just to do our math based off. So we have our distance, which is calculated based off our range sensor. We have our error, which is also calculated based off of distance, and our set value. So our set value is just our desired position. And we also have our previous error, which is used for integrals, and it's used for our derivative as well. So next we have if our running. So this is just for me to run the PID. So you want to press a button on your controller and it'll start running your PID, and this is just a default servo position, but this does get changed. We initialize our FTC dashboard. So telemetry is equal to new multiple telemetry. You're graphing your telemetry, and then you're just getting the instance of the telemetry. Next we have our hardware maps of our balance servo and our range sensor. After this we start a timer, which I will explain why. We have, in our initialization, we just set the position to 0. You don't have to do this, you can set it to wherever you want, wherever you just want it to start. But for testing purposes, I'm just going to set it at 0. This is your standard wait for stops, just until the op mode's active. So this is where the actual PID code is. So I'm going to go over what this means. So while, or if gamepad.a running is equal to true, if gamepad.b running is equal to false. So later in our code we call if our running. So our PID is actually only initialized, or it only starts taking over the system and trying to get the ball to the position if our running is true. And we just want it to be mapped to a gamepad button. So as soon as we press play, our PID doesn't start running, but as soon as we press A after play, then our PID starts running. We have our current value, which is not used. We have our distance, which is just getting the distance from our range sensor. We have our error. So this is the first important part of a PID. It's our error. So our error is just our actual position subtracted by your desired position. So it's how far away from you from where you need to be. So let's say I want to get to 50 feet, but I'm 25 feet away. So 25 feet. So my error here is 25 because 50 minus 25 is 25. We use this, and we use our gains, as I've said earlier, all in combination to control the servo. So as soon as you press X, the servo position is set to 0. So this is not actually a part of the PID controller. It's just to reset the system. So our P error is calculated off KP times error. I'll go into this in depth later. I'll go through the math later. So you can just, if you just want a PID controller that works, you can just copy our code. The link's in the description. If you have any questions, you can also email us about this. So you have PID D error, which is calculated KD, which is your gain. So your D gain is multiplied by your error minus previous error divided by the milliseconds. So I'll go into what the D does, what your derivative does, and why it's done like this later. We set the position to our servo position. So it can be set anywhere, I guess. We also do change the servo position all throughout based off of our total system's error. So we do calculate our total system's error by just multiplying all of our errors. And this is a short threshold. So as I talked about earlier, your system never actually gets to your desired position. You're always, 0.001 centimeters off, or you're always 1 centimeter off, or your sensor is inaccurate and you think you're at your position but you're not actually, or you're at your position but your sensor is not able to detect it. So I set a small threshold. So if -2 is less than error and error is less than 2. So this means if it's too short of our desired position or it's too over our desired position. So if it's within the range of 4 centimeters of our position, then we just set the errors to 0, which will automatically stop our controller because there's nothing to fix. Otherwise, we increase the I error. So this is to get rid of steady state error. I'll go into steady state error later when I show you how to use the FTC dashboard. We calculate the I error based off of your I gain multiplied by error plus your I error. So you're just reusing it. So think of this like memory, because you're using this twice here. It takes this value and it just uses it again. So it looks into the past and makes changes based off of that. So if you're consistently, let's say, 1 short of reaching your desired position, if you're 1 centimeter off your desired position, eventually your integral will add up and it'll correct your system to get you to that position. So this gets rid of steady state error. And then you set your servo position. So you're probably wondering what this myMap function is. So I've defined a short myMap function. So basically what myMap does right here, I'm just putting it here for just to show you guys, but it just maps your sensor to your servo. So how do you actually know where to move your servo? Like, what angle will your system be at? So this varies per system, so I can't exactly tell you what yours will be. But if you have a motor, you're most likely not going to need this. You're just going to set power to your motor. And for a servo, you might need something like this. So, well, basically, what I'm basically doing here is taking my sensors low, my sensors high, and mapping it to my servos low and servos high. So the servo knows where to move. And then I'm just converting our PID total error into that. And then this actual position is just for graphing. So why do I have a sleep statement inside of my PID controller? Why would I want my PID controller to be slowed down? Well, sometimes your controller can correct something too fast and it becomes unstable, especially in my case, because a ping pong ball rolling downwards can have momentum. And if it's rolling downwards and it has momentum, you're not going to be able to correct it fast enough, let's say. Or you correct it too fast and it has momentum the other way, so it can do very unpredictable things. So I added this sleep statement, which makes it more predictable, but at the same time it's less responsive. So you just have to mess around with this, but a sleep statement does cause the rest of your code. So if you're running your drivetrain in the background, it'll mess with it. But a sleep statement of 50 milliseconds isn't that long, and there are ways to get around this using finite state machines. You can have another timer, and you can only run this code after 50 milliseconds have passed in that timer, for example. That's one way to do it. All of these telemetries are just for me to see. It's just to help me out while tuning, which I'll go over very shortly. Okay, so now I've showed you how to set up the dashboard in your code. Now I'm going to show you how to actually set up your dashboard and how to use it. So first of all, first thing you might notice is you have the option to choose your op modes from here. So you can choose whatever op modes from here. So yeah, it's really convenient. You can just hit the drop down and choose op modes if you have more op modes. So, and then you can just hit init and start. Now your op mode is officially like started. So for my code to actually run, I have to press a button on my controller. So yeah, I just hit it and now it's running. So let me just stop it really quick and restart it. Okay, so now you are wondering, how do I actually graph something? So on the right side, you'll have something called graph. So basically what the graph does is, well, it graphs the two values that you select. So it doesn't have to be two. You can graph however many you want. So I can graph all of these, and you can see all of the values. It shows you what color they were graphed in. So instead of doing that, I'm just going to graph what I want. I want the actual position, desired position. I can set a window. So this is 5 seconds. Let me set it to 10 seconds. Just to show you. It just means this reaches the end in 10 seconds. So yeah, it's no big deal. So another thing you can do is your configuration. So these variables change, and what I'm going to be focusing on today is KD, KI, and KP gains. So I'm going to show you what all three of those do. Alright, so let's get started on the tuning process of a PID. So first of all, I'm just going to show you guys this graph. So this bottom part is my actual position, and this top red line is my desired position. So I'm just going to run my controller and see and let's just observe what it does. So it's okay, it's getting there, and it's really close now, as you can see. So this is known as steady state error, and this is what integral is supposed to correct. So as I showed you guys earlier in my code, as soon as it reaches 18 inches, it should stop, but it's slightly fluctuating down because of the sensor readings, and now the actual position is under. So the PID is going to try to go up and fix it. But if it's in the range within 18 and 20 or 20 and 22, it should stop. Let's see what happens if I change my KD to 0. So first I'm going to reset my system, and I'm just going to let it go. This is without any KD. So you can see the graph looks very different. It's not getting to its position properly, and you can see there's a lot of overshoot here, right? It's going over this line a lot. So what KD does is it tries to get rid of overshoot. So now let me set a small KD value. Let's set it at 1. Okay. Let's see the difference if let me just move this all the way down, and let's let it happen. Okay, the graph does look slightly different, but it's not noticeable. It's like it doesn't make a difference, not enough of a difference. So let's up the KD value to 20, and let me reset the system. Let's go. Okay. So one thing I do notice is this bottom, it's getting higher, so that it's getting better, it's getting closer. So let me up KD a little bit more. So let's run with 50. Reset. Let's go. Okay, so now this is noticeable. You can see on the camera the system's actually making a lot more fine corrections. Like you can hear it, and you can see the servos making a lot of more smaller movements, but KD is still not high enough. So let me try to up it to a high value like 100. Okay, watch. So you can see it sort of stops before it hits the post-it notes, and it does eventually get to a position that is very close to our desired position, although there's still quite a bit of overshoot, as you can see here. So let's try to up it a little bit more. 150. As you can see, that did a really nice job of getting rid of most of the overshoot, but it's not completely perfect. Now it's at its desired position, so it's not going to control anything until the sensor gives a bad read or something. So yeah, that's a nice value for KD, which is 150, so I'll show you my KD value now. KI value. So what does KI value do? So you can see sometimes it does not actually get within the error margins. So what you're going to do is up KI. So it's called steady state error when you're not actually able to completely reach your position. So your proportional controller may slow your system down so much that your speed is pretty much 0 before you reach your actual desired position. So let's say my desired position is something like 20, right? But my KP is too low, so it can only get to 15, for example. That's a problem, and what integral does is it looks into the past, and it realizes that you're at 15 and not 20, and it moves your system up. And KI and KD are constantly in fight with each other. So that's one way to think of it. So now I'm going to set all values to 0. Let's see what my system does now. I'm just going to start tuning from scratch. Okay, now I'm going to run it. Okay, now my system's running. What happened? Nothing. That's because there's no gains, so there's no error, as you can see in my telemetry. That's because the error is calculated based off of the gains. So as you tune the gain, so let's change my KP to 1. Now you can see my P error is very high. So generally when you're tuning a PID, you're going to want to, let me just stop this. So you're going to want to make KP to a value where it fluctuates around your line, where it fluctuates around your desired position. So this is fluctuating very high. So let me try moving KP down like halfway and let's see what happens now. Okay, it's slightly better because it's not going all the way down now. Yeah. Let me lower it even more, 0.1. Okay, maybe that's too low, right? Because now it's not moving at all. So let's try 0.2. Reset. Okay, that's pretty good, but it's not moving at all now still. Let's try 0.3. Okay, so 0.3 is a pretty good value, but it still does not move at all at one point. So let's try 0.35. Okay, so now I notice it's not stopping. Well, it just stopped, but that's just because of my system. It's got a lot of friction in it. But let's just go with KP is equal to 0.35. Or actually, let me up this up a little bit, 0.4. Let's just see. So with KP controller, you're expected to have a pretty big overshoot, and that's what derivative controls. So I'll show you how to get rid of this. So the next thing you're going to want to do is add a derivative. So you can see there's a lot of overshoot on the top over here. So I'm going to change my KD to a value, let's say 50, just a pretty big value. Let me reset. So as soon as I started that, you can see this one's already lower than this. So yeah, just one example, just what KD does. So you can see your KD, it doesn't have a big enough difference. That's because my KD value is not high enough. So let me up it to 100. Reset. Let's see it. Okay, so it actually gets to its desired position now. So here's what I noticed: it went up, went down, and then it got to its desired position. So that's fine, but I want it to be better. So let me reset. Let's see if it's consistently doing this at least. Okay, so it does actually overshoot a little bit still, but it's not bad because, as you can see, it does get to its desired position eventually. So there's 2 overshoots, 2 undershoots, and then it gets to its desired position. So let's see what happens if I up KD even more. Wow, that was actually really good. So it went from the bottom, came up, overshot this little bit, and got into its error margin. So it did a pretty nice job right there. But let's see if I turn it even more up. So 200. Yeah, okay. So it does get to its desired position. There's a lot of overshoot, and the graph looks a little weird now. It doesn't go over first, it goes under first. So maybe this is a little too high. So let me try 175 now. Okay, so this is a little bit higher than it was before, so that's pretty good. And it does reach its desired position, which is really nice. So let me try maybe 170 now. Okay, so 170 does work. It's a little unstable, but it does go up, and there is very, very little overshoot. And there seems to be no steady state error, so let's try it again. Okay, that's really nice. So here, let me explain to you what steady state error is. If my actual position is at 15 and my controller is not going up at all, like it's not able to fix it to 20, then that's called steady state error because there's just a difference of 5, and integral helps get rid of that. There's no steady state error in my system, so I don't really need integral. but I can set it at some super low value, like 0.05, and let's just see what happens. It shouldn't make a very big difference, especially because my system's like has a lack of steady state right now. Yeah, so my system does get to its position, and this isn't a perfectly tuned PID, but it does work. So now let's just try individually. What does a KD do when everything else is 0? What does KP do when everything else is 0? And what does KI do when everything else is 0? Just to individually see how they affect the graph. So yeah, let me reset the position of my controller. So everything's at 0. So let's set KP to 1. So it just fluctuates around its target position. KP 0. So I already showed you the tuning process of KP on its own, so you can just go back in the video a little bit and you should be able to find that. So now KI, let's set KI to 1. It doesn't do anything, or it's very slow. It looks pretty similar to KP in this situation. It's just a lot more slow, and KP is a lot more consistent. So let me set KI to 0 now. Let me reset the ball. Now KD. So let me set KD to 100. Reset, go. So nothing's happening. That's because KD is supposed to stop overshoot, and the dashboard is actually at a position, it's at 5 right now, so it's under 20, so it's not going to do much at the moment at least. But if you had a KP controller, so I believe we went to 0.4, it does do something now. You can see when these two work together, it does get to its set position. So this is known as steady state error, as you can see on the top right here, because it's not exactly at its position, and integral is supposed to help with this. But one thing to note about my system, I have a margin from 20 to 22. So if I show you guys my code right here, here, let me get my code. You guys can see that I have this one if statement that says if the error is within a margin of 4. So if it's 2 less than the error or 2 greater than the error, you set all of the errors to 0, which will just stop the controller, because as I showed you guys earlier, when there's no error, the controller doesn't move. And if it's not in this 2, so then it starts adding to your integral controller. So if it's at 17, you're not at 18. But let's say your proportional and derivative controller are not able to get you to a value such as 18 or 20 or 22. Your I error will eventually add up over time, which will help you get to that position. So that's how you tune a PID. So how our system actually works. First of all, I've already ran the op mode, and I'm graphing 2 things. I'm graphing our actual position and our desired position. So on the top here, we have our desired position, which is 20 centimeters. On the bottom here, we have our actual position, and it looks a little noisy because the ball is curved, so the sensor is not actually able to too accurately calculate where it is. But it's pretty accurate. It's accurate enough for our own needs. And yeah, so I will let the controller run now. So let's observe what happens on the left. Okay, so we see. Okay, let's give it a second to get to its actual position. So now it's at its desired position. So over here you can see they match. They don't match exactly because at one point you can't get to your exact position, and we don't want the controller to oscillate too much. So what I've done is I've added a threshold. So I've added a threshold of about 2 centimeters plus or minus. So if it's 2 centimeters to the right and 2 centimeters to the left, it should just stop, because we're not actually able to exactly get it to any position at any time in any system. Otherwise the PID controller will never stop, it'll continue correcting forever. So let's just drop this again. Let's just look at it. So over here we can see it overshoots and undershoots, overshoots. Yeah. And eventually it does get lowered. And eventually it lands within the error threshold. And we have our PID controller.